And now we are still working on this kind of question with Shuta Nakajima. Also Anna Donadini, who is a PhD student of Francesco Caravenna. And also with Francesca Cottini, who is now a postdoc student in Singapore and in Luxembourg. Francesca Cottini, I hope there are really two T's on her name. Okay. So mostly my talk will be about this kind of okay, maybe I can erase this. Yes, it works. Okay. So my talk will be mostly about 2D objects, but let me first introduce what is a polymer model in a general framework. So it's made out of several objects. The first one is a simple random walk on ZD. So you are on the grid, and your random walk can go to any of its neighbors on ZD with equal probability. And second object will be random variables that we drop throughout the whole space. So don't think only about ZD, but it's actually a random variable both in time and space. So at each time, the random variables are also thrown, and they are all identically distributed with nice properties. For example, exponential moments, they are centered, they are variance 1. And what we define is a tilt on the polymer measure. So maybe I can put some D's here. So instead of looking at the usual law of the simple random walk, we tilt a bit its measure by introducing some rewards that is given by an energy which is given by this sum here. So let me maybe draw a bit of a picture. So we have this object, which is a simple random walk. So here we have ZD here, and here we have time depending then. And then on all the space, we have these random variables distributed. So in a D+1 kind of space. And we throw a random walk inside this space. So it can go up, down, like this. And what we will look at is that the sum of all the random variables that has been seen by the walk. So maybe I missed a bit of them. There are also one like this. So we do the sum of all the walk, all the random variables that are seen throughout the displacement of the random walk. And if the variable omega that are seen through the path are big, then it will give a larger contribution to the probability of the new measure. And if the sum of the randomable are small somehow, it will give a less probability to this path somehow. So it's a probability measure on the path space. So you look really on the whole path Sn here. And the new measure we constructed is called the polymer measure. It's called a polymer because it's basically this black line, which is a random walk line, is basically, you can think about it as a polymer. So it's a long line. It's called a polymer in random environment because of the presence of the omegas. So I think my drawing is very terrible. I'm sorry, I'm not using my tablet, so I hope it's clear. If you have any question, maybe it's a good time to ask if the model was not clear. Okay, I hear no question.
Yeah, I have a question, Clement. Are you considering Gaussian environment, or I mean, okay, maybe it's going a bit for what you're going to say next. But
Okay,
I'm a bit
so it's a
surprised by
good.
this beta square over 2.
Yes, exactly. So here, in fact, you're completely right. There is a beta squared over 2. So the reason for this is because I'm assuming Gaussian weights. Yes. So the omegas are Gaussian. The reason, so there is this minus beta squared over 2. It's just for the normalizing constant which appears for the probability, for the measure on the left to be a probability measure. It's just very convenient to add artificially this constant, because then it makes this object of mean 1. Okay, that's the role of the presence of the beta squared, minus beta squared. If you have random variables that are not Gaussian, then you should renormalize by another constant of beta, which depends on the environment. Thank you very much for that. Is it more clear now? Okay, perfect.
Yes.
All right. So, okay, good reference for this object is the lecture notes by Francis Comet, which give a very complete overview of many results about this model. And okay, maybe I didn't mention, but we have this parameter beta as well, which kind of tunes the strength of the environment. So the higher the beta, the more the polymer measure will be attracted to high values of omega and repelled by lower values. So that's kind of intensity parameter for the environment. And okay, so we can express explicitly what is the renormalizing function. In this case, it's just an expectation. So here is expectation with respect to the simple random walk measure. So in particular, it's an expectation over Sn, but it's still a random variable because it still depends on the variables omega here, right? So this is still a random variable depending on the law of the environment. And I added some parameter x here, which is just the starting point of the random walk. So you can start at any point in ZD, and you can start at 0 as well. But it will play a role a bit later in the talk. So starting at other points has a sense, has a meaning. So so there is a phase condition. It's a well-known result for a long time now that if beta is very large, then you are in a localized phase, in the sense that your polymer path will be concentrated in places of the environment where, let's say, in small parts of the environment where the omegas are very large. So it will be attracted by this part of the environment, whereas in the diffusive regime, when beta is small, then the polymer will act diffusively as of the random as of the simple random walk usually, and it will not really feel, at least at large scale, the presence of the environment. And this can be, in fact, characterized by a limit on the partition function. So this Wn. So whenever the Wn goes to 0, then it will mean that the localized phase, that you're in the localized phase, and if it's strictly positive, then it means that you're in diffusive phase. There are other parameters when you can look, for example, at beta c bar, where you ask a bit more, for example, for the partition function to converge exponentially fast to 0. And okay, it has been proved recently that by Huber here and Stefan Jung, that actually whenever the random walk whenever Wn converges to 0, it actually converges exponentially fast to 0. And in particular, thanks to that, whenever you are in whenever you are in the localized phase, there are many results of localization. So you can prove indeed that the random walk is confined in some very small part of the environment. That was already only proven for beta larger than beta C. But now it's actually proven for beta larger than beta C. It was only proven for beta larger than beta C bar, which was a bit higher, but now we know that they are equal. So we know that the localized phase, that there is really a localization, a strong localization property whenever beta is above this beta C parameter. So just let me tell you a bit about the dimension. So whenever the dimension is 1 or 2, in fact, you are always localized in the sense that no matter how beta is small, you will always be attracted by the large value of omega. And when dimension is large, you actually have a phase transition. So for beta small, you will be diffusive, and for beta high, you will be localized. Okay. So if there is no question, continue. What is okay? There are interesting links with SPDs. In fact, this WNX, so I define it here with also dependence on the space, and you can think n as a time. Then, in fact, it's up to just some reversal in the environment, reverse time in the environment. It's actually Wn of x is actually a model for a stochastic equation, actually a discrete model. You can also construct as a continuous model of polymers, which will also act as a stochastic equation, which is a diffusive. It's an equation with a Laplacian, so you had some diffusivity, and you have a white noise psi on the whole environment R times RD. And the specific behavior is that this white noise is multiplied again by U, so we call it sometimes a multiplicative stochastic equation. So there have been many works in the links between polymers and stochastic equation. It's basically the polymer is the Feynman-Katz formula for the stochastic equation. I mean, the partial function is the Feynman-Katz for the stochastic equation. And in fact, it's also linked to another equation. If you do the Hopf-Kohl transform, you take the log of U, then you arrive quite magically to another equation which has been much studied as well, which is the KPZ equation, where now you have a noise which is not multiplied, but now you have another strange thing, which is a square. So one of the difficulties of this equation is that either here or here, it's not okay. A priori, if you only know that U is a distribution, it's very hard to make sense of the product of two distributions, and that's a big difficulty to make sense of these objects. In dimension 1, it has been done, but in dimension 2, it's really not clear that one can construct these objects. In fact, in these solutions, because of the roughness of the noise, you actually expect that U would be a distribution for higher dimension, and then it's really hard to make sense. In dimension 1, in fact, you can show that U and H are continuous functions. So this is what I wrote. Is for in higher dimension, it doesn't really make sense. But in dimension 1, you can really formulate a link between the discrete polymer I introduced before and the KPZ equation that just appeared. When you take a diffusive limit, so you take a space like square root of n, you take time like n, but the important point is that you actually have to kind of zoom beta to the critical value 0 in dimension 1, beta c is 0. So you have to tune the temperature in a very specific way. So here is how. And if you do that, the limiting object you find is the KPZ equation when you take the log of Wn, because Wn will converge to the stochastic equation, and then if you take the log, you get the Hopf-Kohl transform, so you get the KPZ equation. Okay. And in dimension 2, you can ask the same question. Can we obtain something if we do the same procedure? So if we take time, if we rescale the noise, the temperature. And in this case, if you look at diffusive limits, the way to obtain a non-trivial limit is by rescaling the noise a bit differently. So in dimension 2, you should take 1 over square log n for beta n. And otherwise, okay, in other regimes, then you get kind of trivial limits, at least in the diffusive scale. And what has been proved, I think the first statement it was by Caravenna-Sun-Zygouras. They discovered a bit this transition that I will just show you, is that when you rescale beta n like this, and you have this extra parameter that you can add to tune up a bit the scaling, this beta hat that appears here. Then there is again a phase transition, a bit reminiscent of what happens in a high dimension for the polymer, in dimension larger than 3. You find again a phase transition where when you are below criticality, you have a convergence of the log of Wn to a Gaussian limit. So you can think about this as Wn being exponential of a Gaussian. In particular, this is positive. So like in dimension larger than 3, you get that Wn is kind of positive in the limits. So it's a sort of a weak disorder where the polymer is again diffusive. And when beta is larger or equal to 1, so that's an important point, then Wn converges to 0. So again, you have some kind of strong disorder where the polymer, you can expect the polymer to be localized. An important point here is that in this phase transition that appears, we know the critical value, beta c. In dimension higher or equal to 3 for the polymer, beta c is unknown. I'm not sure if there are conjectures, maybe Huber has some. But maybe it's not even, there is no expression for it, probably. In dimension 2, in this very interesting scaling, you can really find what is beta c, and that's quite interesting. In particular, you can really try to study the polymer model at the critical point and try to understand what kind of features it has. Like, is it diffusive, localized? Is it a bit of both? So there are many open questions about the critical behavior. What else? Okay, I didn't tell you. So in the case where beta hat is strictly less than 1, you have a Gaussian with this lambda squared, and this lambda squared is given by this expression. In particular, you see that when beta hat goes to 1, then lambda diverges. In particular, this is how you prove that by comparison, you can actually infer from that the critical point has to be 0 because of these formulas, of this limit. So okay. No question, maybe. Is it clear? I didn't lose everyone. Okay.
I have a question. Quick question.
Yes.
So I think I remember Caravenna-Sun-Zygouras. So what is the item I think it was proved there, but so what is the these other two works?
Yes, I completely forgot to mention it. Thank you for the question. So okay, the item 1 implies item 2. In fact, so once you can prove 1, you can prove 2. The point is that okay, there was a first proof given by the 3 people here, and then they okay, the proof was quite difficult. What they proved, in fact, was that Wn converges to exponential of a Gaussian. Okay, to the Gaussian which is here. And so they studied, in fact, Wn and not log of Wn. So they didn't prove some kind of central limit theorem. They really proved that an object converges to exponential of a Gaussian, which is, okay, there are definitely less tools to prove that. And so in particular, what they did is they decomposed Wn in chaos, and this in this chaos they found that it should resemble at the exponential of a Gaussian. That was how they did it. And then there was another work a bit more recent by Caravenna and Cotini, where they actually worked directly with log of Wn. And they proved the central limit for log of Wn, but they had a similar approach, which was to say that to find a chaos expansion for log of Wn somehow. So it's a chaos expansion is just a big sum of random variable and powers of random variables. They showed that log of Wn can be approached by a specific chaos, which you can determine completely, and that this chaos could be also proven to satisfy a central limit theorem by using some general theory of central limit theorem for chaos, kind of. And what we did with Anna was to propose a really elementary proof. Like I can really, it's in fact the content of the next slides. So the proof goes as follows. First, you start with a decoupling. So I'm always assuming beta hat, which is strictly less than 1 here. And in fact, what happens is that if you look at dyadic scales, so here is my kind of dyadic scaling. I'm taking n to the power of k over m, and m is just a large constant. And this is, okay, this object is like the partition function we had before, but the partition function we had before was starting at n equals 1 and ending at n equals large n. And now I'm just focusing on a dyadic window. So I'm actually restraining the environment, the dependence on the environment on this smaller size window. And it turns out that that in the initial partition function Wn, all these scales kind of decouple in the sense that Wn becomes asymptotically a product of all these smaller scale partition functions. And that's just L2 computation. We take Wn, we reflect the object on the right, and we do just some L2 computation, which are just kind of elementary random walk estimates. So that's the first step we do. So, okay, you need to work a bit to obtain this, but really it's only elementary manipulations. And then once you have that, of course, if you take the log here and the log here, log of Wn becomes the sum of log of zkm, right? So the log of Wm is actually can be approached by just a sum of logs. And the important point is that all the environments that appear in the zk's are independent for different k's, because the omegas are independent in time. So all these zk's are actually independent in k. And then you can just appeal to usual central limit theorem. Okay, the first thing is to really prove the central limit theorem on this object. We first do some Taylor approximation, because okay, when m is very large, these zk are actually very much concentrated around 1. So there are something of this order. So we can do a Taylor decomposition. And if you go to the second order, you get 2 terms, this one and this one. And zkm are just usual partition functions, so you can easily have estimates on their second moment, and prove that there is a central limit theorem for this one, and for this one there is a law of large number appearing when you take the square, which gives you the 2 parts of the Gaussian law, which was okay. The limit was minus lambda squared over 2 lambda squared. So you indeed obtain the central limit theorem by a very very elementary proof. And so what we are a bit working on now is to try to see how much this strategy can lead to different proofs when, for example, you assume a bit less nice thing on the environment. So if you had some correlation in space, for example, on the omegas, can you still continue to have this proof? What is the correct scaling to obtain Gaussian laws? And so this is kind of work in progress now with Anna and with Francesca.
I have a question.
Yes.
When this proof to use that beta hat is smaller than 1, when you do Taylor? Or?
When you do a second moment of decay, basically, in fact, the second moment of WN blows up at beta hat equals 1.
Yes,
And it's finite before.
Thanks.
In particular, it's the same appears for ZKM. So when you have beta hats, all the random variables that appear here will have a diverging second moment, so you cannot really apply to appeal to local limit to the central limit theorem. But of course, it's still quite interesting to wonder whether this kind of decomposition still makes sense at criticality, for example. Are the dadic windows still decorrelated? Can this lead to some properties for at criticality? I think it could be quite interesting to. I think Francesco, Nikos, and Ronfeng kind of uses similar properties in their paper where they study criticality. I forgot to mention it, but maybe I will come back to it a bit later. Yes. Another question.
I have a question, Clement. So you were just saying that beta hat equal 1 was the L2 threshold for each of the ZKM.
No, not each. Okay, that's a good point. It's really the threshold
just
when K is large is around M, basically.
Okay. Yeah, so
of
well,
course,
yeah, I was just,
not
just
of course,
wondering.
but if you take K small, then you might be able to still have finite moments.
Okay.
K gets large, and then you get into trouble.
Yeah,
And
I was
in fact,
thinking that
it's the same at
M equal to
criticality.
K equals 1, I think it changes the value of beta hat, right?
Sorry? Yes.
If you take M equal to K equals 1,
Mm-hmm.
and then you're basically replacing N by square root of N, so you're kind of changing the value of beta hat, right?
Exactly, yeah, because beta hat is related to time, so you change a bit time, and then you change a bit the critical. Log n is replaced by log of square root n, so you get 1/2 more room to increase beta, something like this.
So when you take the limit when n goes to infinity, these DKM, they are not at all IID, right, in K?
No, and in fact, it's a very important point. The variance is okay. It's of constant order, but it's strictly decreasing. And in fact, it will come back later. So in fact, you can compute. Okay, so that's a very good point. So the variance of the ZK here. Sorry. Oops, what is happening? I don't know. Okay. The variance of the ZKM is in fact beta hat squared over m times 1 over 1 minus beta hat squared k over m. So you see with Taylor, with Riemann sum, this will actually converge if you sum over k. So sum over k of this will actually converge to integral of 1 over 1 minus beta hat squared x dx, which will be exactly equal to lambda squared. Lambda squared was, maybe I should have written it, was 1 over 1 minus beta hat squared. Maybe so it's beta hat squared as well. But you see that indeed the variance profile here is not constant in K, and it will not be constant at the limit as well, because you get this variance profile that is not constant in X somehow. So they are not IID, but the variation of the variance is strictly decreasing, and it's bounded also from above and from below. Was this your question? Yes. Okay. But in fact,
I have another question. Sorry. Yes. So the I remember in Francesco and Nico's Ronfen's paper, they have this decomposition in this chaos decomposition, right? But
In
so
the
this
first paper, you
decomposition,
mean? Like
yeah,
this one?
yeah, exactly. So just at the heuristic level, these ZKM random variables play the same role as this decomposition in chaos, that each one of these chaos goes to some Gaussian random variable, and the sum of the variance is the variance of the final object, or is it a completely different decomposition of
I mean,
the...
I think you can definitely draw some parallels between the proofs and okay, I don't know enough well enough the proof, but I'm pretty sure that you can find again some very similar features from the variance profile, and for some of maybe you can also draw again some ZK, find again some ZKM in a more complex way, in the sense that I think the ZKM that they consider are not exactly okay, I can tell you at least for the second paper, so the Caravenna-Sun-Zygouras paper. In fact, their proof is somehow quite similar, but what they consider is ZKM that are somehow much more complicated. They are like chaos that appear in the chaos from the log of Wn, but somehow they should play a similar role to this ZKM. What I find in our approach is really that we completely forgot about chaos. We just write it as a different polymer partition function. But I think you can find a similar ZK that appears in both the first and second proof somewhere. Okay, the proof are not that different in the end, but I think in the detail, this is a bit more simpler approach. And also the proof is very short, like compared to the other proofs. Yes.
Thank you.
Okay. Okay. So now it comes okay, this for all we saw from until now. You see the starting point of the polymer was always 0. And okay, you can ask what happens if you look a bit. Okay, this function here, Wn of beta x has some interesting features in x. It's right, it's solving a PDE, so it's quite natural to wonder how also space is involved in this regime. And okay, maybe there are many results. Okay, again. Maybe the first one was by okay, maybe the first one was in the same paper here, where they considered the space properties of Wn. But okay, what is more relevant in this always is really looking at log of Wn. But if since everything are actually distribution, it's not easy to say something about the distribution. Okay, if you know something about the distribution of Wn, okay, when I mean distribution, I mean that that this field here, Wn of x, phi of x. So you take space in R2, and this function W of n of x should be quite rough in terms of x. So if you want to study it, you have to integrate it over test function. So you look, in fact, of Wn of x as a distribution. And it's not clear if you know things about this, how to get something about log of Wn. So okay. And okay, I forgot square root n in x. It's x square root n here. Because you take the diffusive scaling. And so in particular, the results that they had doesn't really say much about the integral of log of Wn. And this is really the central object usually in this framework, in this okay, KPZ equation is somehow central, a bit more central than the stochastic equation. And So now if you look at log of Wn, and okay, you center it by this centering, and you renormalize. Okay, you normalize by some constant diverging constant. Then you can find a field at the limit, which is okay. Everything should be integrated over test function to make sense. The limit. Again, I'm working with beta hat strictly less than 1. Then at the limit, you find a Gaussian log-created field. So this is just a distribution where the covariance kernel is decays as a logarithm, and if you test it against the test function, it's a Gaussian random variable. So that's kind of the distribution. So this was very interesting for many people because it was kind of a way to answer to the original question. So in dimension 1, when you took this scaling in space, diffusive scaling and this beta n, you find a non-trivial object, which was the KPZ equation. And the KPZ equation is not a Gaussian object. It's actually quite complicated. The distribution is more connected to the Tracy-Widom law. Okay, there are many interesting features, non-trivial features. And somehow this result kind of tells that there is, in this regime where beta hat is strictly less than 1, there is no hope to find such interesting behaviors in the sense that the limit you find is Gaussian. Okay, it's not a trivial object, completely trivial object, because it's kind of, okay, a lot of things appear for the Gaussian free field. But at least, okay, many people wanted to understand this limit to really show that you don't find again the KPZ equation in this regime. Okay, so that's why there are many results. The first one was Chatterjee and Dunlap. They didn't exactly find the limit, I think. I mean, they didn't prove the limit, but they showed that there was that the HN of X were tight, I think. And then there were like 2 proofs kind of simultaneously. I think this one appears a bit before, but very slightly after the one. But the first, the one of Caravenna-Sun-Zygouras is more complete in the sense that they obtain this limit in all the region beta hat strictly less than 1. Whereas the result of Gu was restricted for in a smaller region. Okay, not okay, like smaller than a constant, smaller than 1. And then there was some extension by Nakajima and Nakashima, who, okay, they were interested in getting also a simplified proof. So they use kind of different techniques, and also they obtain this result for many type of initial condition when you look at the KPZ equation. So that's a bit okay, different things about this, and in fact, I found this regime quite interesting in the sense that there are many non-trivial properties that are satisfied by log-created fields. And so, with Ofer, we wanted really to understand how much, in fact, you can say that HN as a field behaves similarly to a log-created field. So that was really the initial question. Because of course HN itself is not Gaussian. It's given by quite complex function, and it's only at the limit that it becomes Gaussian. So okay, let me maybe continue and to be more clear what kind of question you're interested in. No question, maybe. Okay, I see no one moving, so probably no question. So for example, one of the interests of Gaussian log-created field is that they almost all share a similar behavior, which is related to their maximum. So this is the first result by Bramson, Zeitouni. Okay, 8 decon. Okay, there are different results in the term of how much you know about. How far you know about the maximum, about the behavior of the maximum, and why am I talking about branching random walks? So branching random walks is just you take two random walks and they branch, and or two Brownian motions and branch at a rate, and you're interested in how far does the okay, you can look at what is the position of the particle of the particle at the end of the tree, and you're interested in how far the last particle is. So here, for example, okay, I took S, but it could be many Brownian motions, and you look at the leaves, and you want to know how far all these branching Brownian motion have gone, and at first order, they actually behave like looking at the maximum of independent random walks. But somehow there is a slight correction I think with the constant that appears here, which would be a bit different from what you expect. What actually appears for branching random for independent random walks, so that this branching structure actually creates some non-trivial, but you don't really observe it directly at the first order, but only at second order. And in fact, this phenomena that appears for branching walks was proved to appear in many other fields that are connected to Gaussian located fields. For example, the Gaussian free field, cover terms of random walks, random matrices, and also the zeta function, which is a bit more surprising. But this kind of universal features of studying the maximum as appears in many different fields, and in particular, one natural question is does this also appear for polymers in 2-dimension, at least in the regime beta hat 3 less than 1? So that's kind of the question we were interested in, and it's somehow quite natural for polymers because when you look at the maximum of the partition function, it's more or less looking at the favorite sites of the polymer. And what you want to understand is what is okay, how probable are favorite sites, and around the favorite sites, how is the polymer distributed? So this kind of very okay, kind of delicate question on small localization properties in this regime. Of course, there is no localization at the diffusive scale, but maybe around favorite sites there are some non-trivial effects which are appearing, and maybe you will find it in somewhere in the correction terms of the maximum. So that's a bit the motivation we had. Okay, no question again. This is the conjecture we have now. Okay, the first conjecture we made was a bit different. It changed a bit this time. So the first conjecture was similar to this one. So okay, change t to log n. And then what you would naturally expect is that the correction should be of the order log n. Okay. In our case, the n it becomes log n. But you see here what you actually expect now. So actually, we wrote it in the first paper. We wrote a conjecture, but it was wrong. I mean, we believe it's wrong. Is that the second term should not be of the order log n, but it should be quite different. It should be log n to the power 1/3. And also the constant we expected for in front of the log was not correct. And it should be quite different from the usual constant that should appear here, and also different from what you have for independent random variable, for the maximum of independent random variable. And the reason is exactly is coming from the observation of Ofer, is that in fact the variance profile, if you remember it, maybe it's a bit far away. The variance, no, it's not that far away. The variance profile of this object is not constant. In particular, in the analogy with branching random walks, you expect not to have a branching Brownian motion with a constant, okay, with the variance of bt is not exactly t, but it will be something that has a correction due to this this varying profile in the zk. And in fact, it was proven by Feng and Zeitouni that if you take a branching random walk with a variance, strictly decreasing variance in the increments, then the constant change. In particular, this constant change, and the second order term also changes. It's not log n, but it becomes much larger. So now we expect that the same should appear in our system because we believe that our walks should be similar to branching random walks with non-constant variance. And in fact, okay, the object we believe should be our analogy for simple random walk is exactly this. So this you can add also x square root of n as a start. And this is the sum of independent random variable. And in fact, their covariance profile in X is tree-like. And so this object could be like analogous to the branching random walk with a non-constant variance profile. This is what we expect, and this is okay what we are trying to prove at the moment with Shuta and Ofer, that the maximum should be at least the first order. Here should be this one with a constant that is a bit different from usual branching random walks. Okay. No question again.
Is C1 positive or negative?
I don't know. Let me check here. Probably negative, I would say. I think negative, but we can check maybe in Zeitouni. We are only working on the first order for the moment. Like it's already a bit complicated just to get the first order, because the problem is that the HN is not Gaussian, so you have to work a lot to prove that it looks like a Gaussian variable, and I will explain why it's a bit complicated in this model. So we are only aiming for first order, but yeah, I don't know, but C1 is a good question. Probably they explain in the paper. So yeah, this is what I told you. The strategy is comparison to branching random walk. Well, yeah, I wrote it down here. And the important point is that yes.
Could you comment a little bit on what kind of techniques you're using to sort of know which constant this is for the first order or for the second order?
Yes. So the guess. I mean, you mean about how do we guess what it should be?
Yeah.
Yeah. So the guess is exactly because we know what should be the branching random walk related. It should be this. This is a kind of branching random walk. And since we know the branching random walk, then we can just look at this paper, where they explain what is this, and what is this, for a branching random walk that has strictly decreasing variance, which is our case. So we just yes. So I can actually okay. I can tell you what should be C0 maybe. C0. Okay, what should be C0 in this case? It should be the integral between 0 and 1 of square root of beta hat squared divided by 1 minus beta hat squared x dx. Whereas if this should be the speed, the actual speed. Whereas if the random variable had been if the variance had been constant, then we would have expected C bar, which would have been actually this 1 minus beta hat squared x dx, which is the famous lambda beta hat. So the initial conjecture we had was with a lambda of beta hat here, and then we realized that actually it should not be that, but it should be this, which is a kind of this different speed. So there is a kind of a trade-off between the variance profile and the usual maximum of branching random walk. So there is a kind of variational problem that arises by following the right variance profile and the right maximal path, and you get you can get this C star by a variational formula somehow. And this is the one we believe. Now the C1, I don't know exactly what it. I don't remember what it should be, and I think it should be 1/3, but I'm not even sure if it should be. Maybe it's 1/6 in our case. Okay. I just can tell you about the first order here.
Great, thank you.
Okay. Okay, and the problem again, I mentioned it a few times, is that the Wn are not Gaussian. The log of the domain are not Gaussian. So to understand how Gaussian they are, we need to compute exponential moments of the log of Wn. But remember that in fact, we are not exactly looking at log of Wn as a field, but we are looking at log of Wn multiplied by some square root log n. So in fact, we need to understand moments of the order square root log n times log of Wn. And this becomes, in fact, this becomes Wn to the power of q, where q can be of the order square root log n. Okay. Just a second, sorry, I had a problem with light. Okay, that should be better. So, so in fact, it's quite unusual, I think, in the. Oh, I don't know what's happening. It's quite unusual, I think, in the yes, in the field of polymer to compute. Okay, usually we do moments of partition functions. What we can do is like something like second moment of partition function. Sometimes we can do third, fourth moment and understanding, but usually they start to blow up before you actually reach the critical values. So they don't give much information. In this case, there is a kind of miracle that appears that you can actually really compute this to a power which is huge. It's a q which is square root of log n, whereas usually you cannot even, okay, you can do finite moments, maybe in this kind of scaling regime in dimension 1. But okay, this is what you need to do, and it's technically quite involved. So that was a lot of the work that we have done so far. I can tell you what we obtained. We obtained that the first result we obtained with Ofer was that if the if the beta hat is quite small, so here is much smaller than 1, and whenever q squared, okay, this is more or less q squared, is less than a constant times something depending on beta hat squared times log n. So this corresponds to q of the order square root log n, as we said. Then we can indeed bound the moments, and here is exactly what you expect if log of Wn was Gaussian, basically. This is the energy you want, and if log of Wn was Gaussian, you get exponential of a moment of exponential of a Gaussian, and then you will get something like this. So that was first step, but of course, two major problems is that we were technical problems. We could not go up to the optimal beta hat. So that's quite annoying because there is no reason not to go up to 1 and nothing should change up to 1. And most annoying was that this 1/3 here, it actually prevented us to look at the maximum of the field at the right order. Basically, what we want to understand is the supremum for x of the order square root of n of our field. But because of that, we could do only something like x to the order, I don't know, maybe n to the power 1, 1/12, or 1/6. So really not understanding the maximum up to the optimal diffusive scale. So that was quite annoying, but still, it was the proof was quite difficult to obtain that. And what we could do if q was a bit smaller, so log n over log, it should be q squared, sorry. If q squared was a bit smaller, then we could obtain it for a beta hat. And okay, let me also cite another result, which was that if q is fixed, then okay, this tells that this is of order 1. So in fact, it tells that the Wn has all finite moment in this region, which was not that obvious. And actually, it was proven also by Liconis and Zygouras, but they didn't obtain any estimate on how the moment should grow with q, which is really what we need for comparison to Gaussian. And in fact, that's one problem, but also I think the taking q to infinity is also another problem. Especially one of the difficulties really to push this up to some optimal q. And let me tell you what we believe should be the optimal q. Okay, so yeah, I'm thinking what we want to improve. Also, this was only for Gaussian weights. But there is no reason why Gaussian weights should be a problem. I think this should be quite general. Okay, another thing which is not really a problem, but it's quite annoying if you want to understand the links between Gaussian multiplicative chaos, for those who know a bit about this. If you want to understand the links between this model and GMC, then you get this annoying factor which is a bit too high to really tackle this question easily. Because there are some theorems where when you get to something of order 1, then you can use some general theorems. But when you have this error quite high, then it's less clear how to deal with that. So what we are doing now, and I think what is proven here is okay, everything is proven. We just need to write it down a bit more properly. Is that we could obtain the results up to with Shuta, we could obtain it up to the good threshold in beta hat, and also we could remove this 1/3 that appeared before. That was a bit annoying here. Okay, so this is what we can do. And in fact, we also studied another regime, and also we could do it for any weight, not only for Gaussian weight. And the other interesting regime is in the near critical case. So when you start to approach beta hat is equal to 1, but quite slowly. So in this sense, then we could also obtain some high moments. Also for Q that diverges, but you see, Q is restricted to some a bit smaller scale. So before in the subcritical scale, you can go up to log n, but then you can go for moments up to nu n, and you see nu n is kind of doing the transition between subcriticality and criticality. So when nu n is log n, then you are in subcriticality, and when okay, it should be theta n, not nu n. And theta n is of order 1, you arrive to actual criticality. And so what we expect is that at criticality, you would still have finite moments. But this was really not okay. We could not do that. It requires more work to study exactly criticality. But we get the kind of the transition, and we see how or at least we expect that the Q you can take really decreases as long as you approach criticality. And okay, how we do that, but I'll go very, very, very briefly, is that we use this very nice formula. At least it works when omega is Gaussian. So this is also why we started with Gaussian weights. And there is a very nice formula which tells you that the Q moments are just the number of intersection of Q independent random walks. And somehow what you need to prove is that each one of these couple here behaves independently from the other, so that this will become something like the second moment of Wn squared to the power Q choose 2, because Q choose 2 is a number of couples, and this will give you exactly this Q choose 2 here. And the expectation of Wn is actually exponential of lambda squared. So that's the idea. The idea is that in this regime, the number of intersection of couples actually behave independently. And that's what you need to prove. And what we do is we expand this exponential. You have sum of sums, and you have to show very carefully that these kind of sums don't blow up, and that they give the right exponential Q squared order. Okay, this is also quite interesting on its own, because this formula is actually related to delta Bose gas models, where the gas particles are actually simple random walk, and they have this potential. And okay, I just said it, but when omega is not Gaussian, the formula is a bit less nice, so you have to work a bit differently to study it, but not that much different. Okay, yeah, let me skip that. And okay, what we also proved with Ofer is the lower bound in another paper. Now we can do for any Q of order log n, and we obtain a lower bound matching up to first order. And what we proved, and this is not really far from being optimal, is that when Q is really too large, so instead of looking at log n, you could look at log n squared, then the moments start to blow up completely in a completely much faster way than what appears here, right? Because here you are looking at the exponential log n, whereas here you're looking at exponential n over log n. So if you take Q a bit larger, so your log n squared is not much larger than log n, then what you expect is that the moment should start to blow up. In fact, I think that this should be in fact the threshold. This is my guess, that above this threshold in constant stress atom log n, then the moments should start to blow up. And this is really kind of related to the random walk, to the branching random walk picture, where this profile is actually appearing in a critical way. Yes, so this is really a question what is the right scale where the moment starts actually to blow up. And in particular, it's an interesting question for delta Bose gas. Okay. Yeah, so what is the optimal threshold? Removing this error term in the exponential, that's the question we have left. And then obtaining the estimate on the maximum, we believe that now we have an upper bound. The upper bound is a bit, again, it's a bit more complicated than usual because of the non-constant variance. But we believe we have upper bound, and now in this case, the lower bound should be quite similar. So we hope to be able to complete it soon. And okay, interesting question that are left is links with GMC, in particular, since the variance of the branching monomorph is not constant. Should we still find a GMC, usual GMC, or should we find a GMC a bit different with different self-scaling behaviors? And also how much all this can have some interest at beta hat equals to 1? Can we still like draw some some parallel between the subcritical case and the critical case in everything that we have been studying so far? But that's very less clear. Okay, so thank you very much.
Thank you very much, Clement. So there has been a few questions during the talk, but are there any more questions? No more questions? Milton?
Quick question about the law of the invariance. So you said that you were considering Gaussian at the beginning, but what about changing Gaussian for other laws?
Yes, so that's was what I briefly mentioned here. So here in this work we really don't need anymore the Gaussianity. So I think once you can get the moments without the Gaussian assumption, then you don't need anymore to suppose that the omegas are Gaussian. That was the only technical limit so far. So I think it should not appear anymore later on. And also weights should not change anything to the behavior. Otherwise, as long as you have, for example, exponential moments. Of course, you can ask where it should break, but this I don't know.
Yeah.
Any other question? Okay, so if not, let us thank Clement for a very nice talk, and good lunch for those who are in South America, and good evening for those who are in Europe.
Thank you very much.
Bye-bye.